In this video, we're going to talk about data and statistics. This will introduce our course, give us a good foundation to work with. First off, understand that when we make decisions, whether it's in economics or many other disciplines, we do so with incomplete information. We always want to make the right decision, but we're limited by the information we have. For example, if you were going to go to a movie tonight, you would probably be well advised to watch the movie trailer that you're considering or read a synopsis of the movies that are showing before you make a decision. That means that you'll get closer to a better decision if you collect a little bit of information. But it takes time to do that, which means information is scarce. It's something we have to produce. And if you're just going to the movie, you probably aren't going to spend a whole lot of time researching what movie to see, but you'll take a little bit of time. Now, if you were going to buy a new car, probably spend more time collecting data because that would be a much bigger investment and it might be worth incurring the additional information costs. Imagine if you're buying a house or planning on having kids. These are decisions that you want to make with a lot of information. The key point, though, is that you'll never have complete information. You're always operating with information that is incomplete. In other words, there's more, but maybe you just don't find it worth the efforts to collect that extra info. These are some examples of questions that we might ask ourselves in economics and finance. You face this one. How much money will you make if you graduate from college? Well, what did you do to answer this? Some of you know people, you've talked to people that have the degree you're considering going into. Maybe you talk to a counselor or professors in the field. They can help give you information. Maybe you went so far as to go to the Bureau of Labor Statistics website and look at the data that they've collected on actual college graduates with certain degrees and their commensurate incomes. Regardless, you know that the information helps you make a better decision. Data are figures used to study something and make better decision. Data is information. And we can think of data here in four ways. There's what we call elements, which are the entities on which data are collected. For example, down here we have some nations that are being looked at: Armenia, Australia, Austria, and so forth. So these would be the elements on which we're collecting data. Variables are the characteristic of interest. So these elements have variables: their World Trade Organization status, their per capita gross domestic product, and their Fitch bond rating. Observations are the set of measurements obtained on an element. So for example, we look at Australia here. This is an element, and then we see these three variables. So this constitutes one observation. And then the data set is all observations collected for the study. Armenia and its variables, there's one observation. Australia and its variables, there's another observation. So on and so forth make up the complete data set. When we measure data, we can think in terms of whether the data is categorical or quantitative. Categorical data is usually involving labels or names, sometimes called qualitative data. There's no mathematical operations when we're dealing with categorical data. For example, boy versus girl would be categorical data. And this limits our ability to do statistical analysis. It doesn't eliminate our ability. You'll find that we often use a lot of categorical data, but it does create some additional hurdles that we need to overcome in order to utilize categorical data. The other way to look at data is quantitative. If we're looking at quantitative data, we're dealing with numbers. Those numbers can be discrete or continuous. Discrete means countable. In other words, there's nothing in between. If we're looking at children in a typical household, we can say there's 0, 1, or 2, or 3 children. But we would never say there's 2.5 children in a household. So it's discrete because it's countable without meaning in between. Continuous data, in contrast, does provide meaning across a range of numbers. For example, weight is often a continuous piece of data because you could weigh 150 pounds, you could weigh 151 pounds, or somewhere in between. The decimal places can have meaning with continuous data. When we're dealing with quantitative data, whether it's discrete or continuous, we're better positioned to do mathematical operations. So this provides extensive statistical analysis. The questions that come up with quantitative data are how much of something or how many of something. So it's very useful. And we'll find in some cases, we may actually take categorical data like boy, girl, and turn it into quantitative data by assigning values like 0 for boy and 1 for girl, things like that. Another way to measure data is whether it's numeric or non-numeric. Data that is categorical can be numeric or non-numeric. As I just described, we could take boy, girl, which is categorical data, and that would be non-numeric, but we can also assign a number to boy, girl, and turn it into something numeric, 0 for boy, 1 for girl, that kind of thing. Data that is quantitative cannot have non-numeric components. It's always numeric. The scale of measurement with data also is important. Here we have 4 ways of understanding scale. Nominal involves labels or names. So we might say that when it comes to employment status, someone is employed or unemployed. When it comes to race, we might say black, white, Hispanic, Asian, among other categories. Nominal means to name something. So that's one scale. Another scale we might use with data is ordinal. This is where we rank something. For example, freshman, sophomore, junior, senior. These are titles that are given to your different class levels, but they're ordinal in that the order does matter. With interval and ratio scales, we have similarities. They're both measuring the distance between data points. For example, temperature. If we look at 50 degrees versus 100 degrees Fahrenheit, that's a difference. And those distance between 50 and 100 matter. Similarly, if we're looking at someone that's 3 foot tall, like a kid, versus someone that's 6 foot tall, a grown adult, then those differences matter for comparison. So both interval and ratio share the fact that the distance between data points does have meaning. The difference lies in what we can do mathematically. With interval data, we can't multiply and divide for comparison purposes. For example, comparing, 50 degrees Fahrenheit to 100 degrees Fahrenheit, you can't say that it's twice as hot at 100 than 50. A student that scores 1,000 on the SAT does not do twice as well as the person that scores 500 on the SAT. As such, interval scale is limited in the mathematical comparisons that we can make. With ratio, we don't have that same issue. And the reason is that 0 is the reference point. For example, if you look at time, if it takes you 2 hours to do something, that's 2 hours above nothing. If it takes you 4 hours to do something, that's 4 hours above nothing. Therefore, you can say 4 hours to do something is twice as long as 2 hours to do something. Look at height. If someone is 3 foot and someone else is 6 foot, you can say the 6 foot person is twice the height. If you pay $10 for something and later on you pay 20, you're paying twice as much. It all comes back to the fact that 0 is the starting point for comparison with ratio data. So we can do those kinds of multiplication and division comparisons. Now let's take a look at collecting data. When we go out and we collect data, it's either going to be time series or cross-sectional. Time series data is data across time. For example, here we have the U.S. average price per gallon for conventional regular gasoline from January 2012 to approximately January 2018. And you can see on the vertical axis here the average price per gallon. And time series data is very intuitive because we like to think about changes that occur over time. So this very quickly illustrates that the price of gas, at least over this time frame, has trended downward. Cross-sectional data, in contrast, looks at a point in time. And we already looked at the example of our nations from before. This would be time series data. So we're looking at our observations for Armenia, Australia, Austria, Azerbaijan, and Bahrain at a point in time. It doesn't tell us here, but if you were to delve further, you might find that this data, these observations, were collected, let's say, January 30th of 2015. It's not across time, it's at a point in time. Now let's take a look at data and statistics. Statistics is a process of collecting and analyzing and presenting data. And it has descriptive elements as well as inferential elements. The descriptive part of statistics is just summarizing data in a variety of tables and graphs. Sometimes you'll do this if you're doing a presentation for a class or for your job. You just want to provide information to people through a simplified illustration. And we'll talk about some of these illustrations in a bit. Inferential statistics is where we use sample data to infer characteristics of a larger population. This is what the majority of research statistics is all about. We start with a population, which is a collection of items under investigation. Let's say I want to know what the average income is in San Diego. Well, my population would be San Diego because that's what I'm trying to investigate. But it's unrealistic to go out and ask every person in San Diego how much they make to get to an average. So I collect a sample, which means maybe I randomly select 100 people from the millions. In San Diego County, there's probably 3 million people, so I select 100 for my sample. The sample, as long as it's random, will be representative, which means this 100 group here of people will represent the larger population with a slight margin of error. But it's certainly more efficient and cost-effective to ask 100 people how much they make than 3 million. And so most research does just this. A random sample is technically only random when every single person in our population has an equal probability of being selected in the sample. So if I'm looking at 3 million people, they'd all have to have the same odds of being randomly selected as part of the 100. That means kind of putting everybody's name in a hat and drawing them randomly. A parameter is a specific characteristic of the data collected for the population. That's what we're trying to get to. I want to know what the average income is for the population. I want to know the parameter. But I don't have it because I'm not going to be able to ask the whole population. So I have to use sample. And the average income that I get from the sample is called a statistic. So we use statistics to get to parameters. On the rare occasion that you don't collect a sample, but instead ask the whole population, that's called a census.